So, welcome everyone to the second session of the November lectures. There's two workshops running this afternoon. So this one and Emily Rochette is running at the same time, and both of the sessions are recorded, so you'll be able to, you know, be here for this one and watch the other one later. I'm going to start by acknowledging that at least I'm on Wurundjeri country. I'm in at work today, and University of Melbourne is on this campus is on Wurundjeri land. I think that the session today, or I hope that the session today really respects that long cultural tradition within many Aboriginal nations, many Aboriginal communities of sustainability, to be able to have a continuing culture for 50, 60, 70,000 years means that sustainability has to be totally ingrained within your cultural behaviour and every part of your activity. And I think this is something that will be ingrained within the upcoming VCE Chemistry study design, and it's something that Seamus has been working on for ages. So Seamus, I've known Seamus since I met him in his staff room about, I'm going to say about 15 years ago. And Seamus is his staff room at Melbourne High School. But now Seamus is a science education lecturer and researcher at the School of Education at Deakin. He's worked as a classroom teacher, head of science, head of e-learning, a teacher educator and a researcher in Australia and Switzerland over the last 15 years. Seamus's research interests are chemistry education, the incorporation of augmented and virtual reality into teaching and learning, and science education in out of school or informal learning contexts. Seamus is presently involved in an ongoing international interdisciplinary project with chemistry and education researchers that focuses on the stuff that we're going to be talking about today, positioning chemistry as sustainability science. And there are many teaching and learning resources from the website that Seamus and his group have created, the Elements of Sustainable Chemistry, which I'm sure will be in the chat. If it's not in there now, it'll be in there in about not very long, and I might put it in there. So that's an interdisciplinary group that he's co-established with other researchers at Deakin. So Seamus, thank you very much for agreeing to present today, and I'm going to hand over to you.
Thanks, Mick. And if you are despairing before you do, maybe make me a co-host, because
yep, I will.
I can share, but I can't do breakouts if we do that. I'll share my screen. So hopefully you can see that in the slide now. So yeah, thank you again, Mick, and thanks everyone for coming.
I just got here 5 minutes ago. Okay.
We'll have a fair bit to go through. I always prepare way too much. So I'm going to start by, well, first of all, I'm also going to start by acknowledging that I'm also presenting on land for Wurundjeri people and the traditional custodians of the country in which I live and work. And I recognise their continuing connection to land, waters and culture. And I pay my respect to their elders past, present and emerging. And then the second thing I'm going to do is I like to always know who's in the audience, because it sort of helps me to know which slides to skip. So if you're interested or not, if you're able to, I'll put the link in the chat as well, and you can that'll make it easier for you. So I'll put the link in the chat as well if you want to just quickly tell me where you're from. I know this year, being on the committee for Chemistry Education Association, I think we did throw it out to pre-service teachers. As Mick said, I'm also the chemistry pre-service teacher here at Deakin. But I have told all of my pre-service teachers not to come to this session, to go to M's session, because they've probably heard me say this before. So hopefully they have. So, you know, yep, mostly secondary, a couple of university regs. I bet that with Mick. And yeah, that's okay, Megan, no problem at all. Secondary, okay. I'm getting the feeling that we're almost all secondary. No one from education, no one from DEET or industry, no, not yet. All right, well, okay, looks like most of us are secondary. As Mick alluded to, yeah, I was a teacher at Melbourne High School for a while before I was sort of seconded and then stayed at university to do pre-service teacher education. So, and I was involved with the previous study design, the quick and review panel, and I've pushed a few little bits of bread Maria's way to try and give some advice, but I'm also looking forward to seeing the study design in the next few weeks. Lakshmi, that's you, I thought it was. Let's keep going. So what we're not doing today is any hands-on practical activities. When we ran this session, similar session last year, we tried, we did. I'm not sure if anyone was here, but we made a aluminium air battery just using some household products. And I thought that went pretty well, and we all held up our thing at the end, but we're not doing that today. Instead, I thought I'll try and cover a bit of, you know, really the things that have changed even in the last 12 months in terms of some of the resources that are out there for looking at material space of society. I thought I'd throw a few stats and figures and graphs your way. I have already put a copy of the slides in the chat. I put it at 4:03, so if you came a little late, you might not have got it, but someone remind me to put it at the end as well. They've changed how you drop files in a Zoom. It's really annoying now. It's like you've got to put it in a Dropbox folder first anyway. But I've put it there, and of course, you can use any of these slides for your own purposes. Who are we? Mick said this already. Elements Sustainable Chemistry. We make a lot of resources, and we love going out to schools when we can. We haven't done it since early 2020. We were at a school, Bright P12, I think the week, first week of March, and by the second week of March, we were all closed down. I think, just taking a step back for a second, the reason why sustainability and sustainable development has been probably such a core focus of a lot of chemistry education research in the last few years is because a few people have noticed what we're describing sort of this untenable disconnect between what we teach in the chemistry classroom and like the content and what's in our study design, and the disconnect between that and the global challenges that we're seeing in society today. And yet, this should be more logical. Like I said, for a long time, when we've looked at, you know, knowing research into what's going on in the classroom and how students learn and how teachers teach, we've often focused on, you know, the levels of chemistry, the symbolic, the language of chemistry, having observations, this submicro level, which is a whole nother area of interest, looking at how students and teachers explain what they can't observe. Professor Peter Hafey, about 15 years ago now, sort of put out this idea about humanizing chemistry education. And to Johnston's triangle, he introduced the human level, sort of making it a tetrahedron, thinking about how it is that we can talk about the things that we're learning and connecting in society. In the last few years, we've been pushing that a bit further. We're saying, no, let's make those connections more explicit for students. The social factors, economic factors, environmental factors, these are the things that students should be learning. Because, and this is the fact and figures bit, because we are, this came out last year. This is in Nature, you know, it doesn't get much bigger than this. Global human made mass exceeds all living biomass. And so I'll skip the quote and I'll just show you the graph. This is from that thing. Of course, I've got the link down the bottom if you're interested, but this is straight from that report showing you the anthropogenic mass in 2020, give or take, we crossed the dry biomass level. So to put that in another way, and so you can see it there, you know, concrete, gravel, that's really the bulk of it. But, you know, even metals, you know, other plastics are there. to put this another way, if there were 4 gigatons of living biomass, so all our animals, all our species, that's 4 gigatons. There are 8 gigatons of plastic, just plastic. So, you know, we've already got twice the amount of plastic as we do living biomass. Trees, shrubs, you know, that obviously that makes up the bulk of all biomass in the world. And yet here is buildings and infrastructure having more of that. So you know, we're really at this point. How did this happen? You know, chemistry is the study of, you know, analyzing, synthesizing and transforming matter. You know, we are the science of transformation of matter. So clearly chemists had a role in this. And so chemistry education, therefore, has a responsibility to teach and address the response, this matter. And are we doing a good job? Well, that's questionable. You know, we can't blame this all on chemistry educators, that's for sure. But, you know, there's many examples of, and I'll show a few later, but this is just one, of materials that certainly as chemists and as chemical engineers, we have developed those materials and they've led to many, many great discoveries and advances in society in the 21st century. Yet perhaps we weren't considering the whole system. You know, nurdles, they're not considered toxic, yet they clearly are. They're not banned, yet perhaps they should be. And yet here's an example of a story. It was in Guardian just a couple of days ago, looking at, you know, the worst toxic waste material that perhaps you've never heard of. So that's the bad news story. The good news story is that the Royal Society of Chemistry put out a report again, very recently. I'll put a link in the chat in a second, but the link's down in the slide, where, you know, they did a huge survey of students of different age groups, educators of those different age groups, and it really confirmed to them, and it should also confirm to us, that young people expect to be educated about this. They expect this to be in their curriculum. So, you know, next time you hear a teacher going, oh, well, you know, we can't, you know, there's too much to do. There's a crowded curriculum. We have to get through all these things. It can't be assessed. Bollocks to that. Who cares? Our students expect to be educated about this. And so that really should be the, you know, 79% seeing it as a priority for a chemistry curriculum. The educators say the same thing. Like I said, it's not as if they're going, oh, well, that's just students, you know, students. But no, this is a study of the entire UK, you know, anyway, but across the different age groups, 65 to 70% of all educators said that there was too little chemistry content covering these areas of sustainability and climate change. So really, I think we need to dramatically increase the amount of stuff that we have in our curriculum because teachers are asking for it and so are students. When they asked them what particular bits were interested, these are the 3. So the top 3 ones, so they ran a survey, gave them all different options, and these are the top 3. Carbon literacy, so that's the idea about, you know, the relative impact of different sectors, individual actors and how they contribute to climate change. That was number 1. Life cycle and impact of materials was interesting. You know, life cycle analysis, thinking about ins and outs, feedstocks and so on. And then the finite nature of resources. That third one sort of been a big focus of some of the teaching and learning resources that we've been developing through our Elements of Sustainable Chemistry site. And we've been doing it with systems thinking. Now, I thought today I wouldn't do much systems thinking content. I sort of did it last year, but I thought I'd show a few examples how systems thinking could be used to do this. So I think I've just got this one slide and we'll get on to some of the more chunky sustainability stuff. Why systems thinking is so great? Well, you know, systems thinking helps identify the interactions between a system and its environment. So what I mean by that is rather than thinking of just a simple nitrogen cycle or carbon cycle, but actually thinking about the relationships between parts of that and recognizing that, you know, all of those parts, they have an impact on that system. So the parts have an impact on the system and the relationships between parts has an impact on that system. It's very easy to sort of think about how we could assess each part of a system and then maybe build a bigger picture. But sometimes that loses the finesse of how two individual parts, how they interact with each other, and how that changes the entire system. Also changes over time. And so, sometimes we look at very small timescales and very large.
I'm not a chemistry lecture.
And they have very different impacts on a system. And then getting into the nitty gritty, thinking about variables. So, causality, granularity, feedback loops. So examples of ocean acidification is a great one for this. So having a look at ocean acidification as a systems perspective, as opposed to simply quantifying all the different parts, you come to a very different conclusion as to the impact of humans on this environment. I gave a talk at StavCon and I focused on this a bit. And at StavCon, I was perhaps thinking more sort of lower secondary, but I thought I'd show this to you as well. StavCon was last Friday. How would you teach global cycles differently if you were thinking of a systems thinking approach? I took these pictures from a fantastic website. You should really go have a look at it yourself. sciencelearn.co.org.nz. I can see a few people nodding their heads, so perhaps you've been there. But it's a fantastic site for all different parts of a science curriculum. And here's just a few examples of looking at different cycles. But if you look at it, some of these cycles, they can somewhat downplay the impact of industry, the impact of the interactions between humans and industry in these cycles. And so when we look at the planetary boundaries framework later on, I want you to perhaps rethink about nitrogen fixation and how you consider that the nitrogen cycle separately when teaching in the lower secondary or maybe introducing it in equilibrium, but how would you do it differently if you were focusing on the human interactions of that system? I'm going to take a breather in a second. So the one thing we did last year, and again I won't focus on it this year, was thinking about Sustainable Development Goals. As Mick alluded to, I'm involved with an international project at the moment, developing a teaching and learning framework for the International Year of Basic Sciences in Sustainable Developments. It's quite a mouthful. It's IYBSSD 2022. So we had the International Year of the Periodic Table 2019, the International Year of Basic Sciences and Sustainable Development next year. So there's not much out there yet. It's still pretty early. The official launch, I think, is sometime, it's December now, isn't it? Sometime next month, but they generally start putting a lot of things online in February, March. So definitely keep a lookout for it. And so one of those will be, because after all, the United Nations are pushing this pretty hard, for us as educators to make sure that our students are aware that everything we do should be towards addressing these 17 goals we set for ourselves. Here's something you could do with your students. So we did this with a group of chemistry teachers last year, working in a professional learning program that the CA fund, and I mentioned last Wednesday. The systems maps. So again, let's say you put a chemical process in the middle. So one example on the left was, this was a class of students who were looking at the Haber-Bosch process. And so wasn't it so fantastic, Doug McFarlane's talk last week? Well, that's exactly this one here, thinking about sort of the Haber-Bosch process, the massive generation of ammonia required for fertilizers, but also even as ammonia as a fuel, all the sort of things that we use ammonia for. And so here is an example of that reaction. You yourselves have probably taught that when you've introduced equilibrium. Maybe you've shown it with low yield levels, balancing equations, writing out a chemical equation. So it's one you know well. But here's how we connect it to, you could encourage the students to go, tell me everything you know about it. What is the ammonia used for? Where do they get the nitrogen and hydrogen from? And then add to that, how do each of those different little boxes of your map address the Sustainable Development Goals? Are they a positive influence on those goals? So in other words, that part of your map is contributing to meeting the goals in 2030, or is it impacting negatively the goals for 2030? The example on the right is another one where quite literally you take each of those goals and you map it out in terms of their connection to chemistry. And so the example here is, again, nitrogen. And so looking at all the ways that nitrogen is present in each of those goals. So again, fertilizers, so nitrogen-based fertilizers are probably a number 2 type of fertilizer after phosphate. And so massive amounts of fertilizers are required, dramatically make it more possible for us to have zero hunger by 2030. And so therefore no poverty, and therefore good health and well-being. But the inverse of that is producing too much fertilizers is irresponsible, so that fails to meet the SDG 12, which is responsible consumption and production, which has a negative impact on clean water and sanitation, life below water, life on land, and so on. So that's really an example of what you can do, mapping out those with it. Just a few student examples. This is an example, Beck, if you're in the audience, a class of students looking at polylactic acid and connecting it to, and so looking at all the different colors and positives and negatives of PLA. And so, yes, it was an online activity for them, but you imagine doing a prac with PLA and then doing this as a follow-up to connect chemistry with the Sustainable Development Goals. Another example was doing it with ocean acidification. And so here a student can start to really see not just the connections between each of the steps of ocean acidification, but how they impact different parts of either the atmosphere or the aquatic environment. So I'll just leave that slide there. I think we won't do it, actually. I'll give you more time to play with the Planetary Boundaries framework in a moment. But you can go in and you can copy those links to your own delight. They're just Padlets. So we made, I did it with some teachers here, and I've done it at a couple of conferences now. Just, you can go in and copy those Padlets yourself. We made one for plastics, for fertilizers, for concrete. So there's some examples there that encouraging you to have your students connect what they're studying in the chemistry classroom with those Sustainable Development Goals. I'm skipping that because I want to give you plenty of time to play with this next one. It's really a big focus of what we're doing with the International Year of Basic Science, with the IUPAC project working group that I'm involved with, is the Planetary Boundaries Framework. Now, who has heard of the Planetary Boundaries Framework? You can just put a response, or you can throw something in the chat. I've always wondered how much of this has got out. Maybe you saw there was a Netflix thing about it earlier this year. It's called Breaking Boundaries, with our Lord and Saviour David Attenborough. He was with Jonas Rockström. Carolyn saying no. So yeah, okay. So it's a bit of a no. So let's go through it. So the Planetary Boundaries Framework was first proposed. Yes, Guy, that's where we're going here. So it was first proposed about 2011, if I'm right. It might have been 2010. People like Jonas Rockström and Alan Steffen, who is actually still here, Mick, in Australia. He's at ANU, I believe. And so them and a huge team of people like at the Stockholm Resilience Centre, they took a huge amount of metadata, and then they were looking at setting boundaries and so these 9 different conditions. And basically, if we stay in the green zone, we can be relatively assured that, whatever random thing happens in the future, we will still be able to keep the planet in control. So in other words, we're not having a negative impact on our environment. But we start to push into the orange, and we start to limit our ability to control what will happen. And so when we get into the red, essentially that's Mother Nature putting her hands back on the wheel, and we know humans no longer get a say in how the Earth systems work. You know, we're just along for the ride at that point. We will not be able to do anything to steer the ship back towards the green. So red is bad. Red is very bad. And we're fairly confident, again, looking at, this is massive amounts of data that goes into these studies. We're fairly confident that for biosphere integrity and for biogeochemical flow, we are well and truly in the red. We're well past where we should be. Some of the other ones, we're in the green, but we're heading in the wrong direction, and some of the other ones, we're already in the orange. So what does this mean? You know, it basically means that, no, that's right. It basically means we're not controlling the Earth, and it will substantially change, and we don't know what happens next, and that's a concern. So it's time to go play. Before I go through some of the ways that you could use the Planetary Boundaries Framework in your classroom, I thought you should go play with the Planetary Boundaries Framework. So what I thought might be a good thing to do, I'm going to put the link directly in your chat. Before you go off and do that, I think just go play for 5-6 minutes or so, and then come back and I'll show you a few things about it. But before you run off, I really need to say a huge thank you to Professor Peter Mahaffey. Professor Peter Mahaffey is at the King's Centre for Visualisation and Science in King's College in Canada. I've borrowed a few of these slides from him. He's very generous. He's the task group leader of the group that I'm with, the IUPAC, and Sarah Connell, who has had, from the Stockholm Resilience Centre, who's had a fairly big role in some of the behind the scenes stuff that's happening with the Planetary Boundaries Framework. So I'm interested to see what you think of it. We are making modifications of it at this very moment. I've got a meeting at 6 a.m. tomorrow morning to talk about it. So I'm interested to hear what you also think about it. So go play. Mick, did you let me do, are you still here? Are you going to do breakout rooms?
Yes, still here. I think you're a co-host, so I think that means you can do breakout rooms.
So let's do, say, 4 breakout rooms. Seems about a good number. For 5-6 minutes, go play with it. I've put the link in the chat. There's many things you can play with it. You know, click, drag, scroll, click on tabs, have a play, and tell me about it in 5-6 minutes time.
All right. Do you want to, can you make the breakout rooms, or do you want me to?
I have.
Okay.
Oh, I've got to open them first. Here we go. They're open now. I'll hang around here and take any questions if you want to. Oh, you came back early?
It said 47 seconds. I thought I'd, you know,
Like,
we got the notice.
So you know, normally everyone comes back sort of half sentence because someone's been talking over the 3, 2, 1, and then.
We're trying to get back before the electricity fails with the storm.
Yeah, it's really bad. I've already cut out once, so I'm hanging on for dear life.
Oh, I when you went to breakout rooms, I called home to tell my mother picks up my son on Wednesdays and said, don't bother going to tennis because it's been cancelled. Yeah. All right, I think you're all back now. So yeah, hopefully you all had a nice play. In case you didn't, I'm going to just quickly show you a couple of things. Which one do I want to show you? I want to show this one. Yeah, so look, everyone sort of notices that eventually they sort of see how, you know, again, looking at how it's changed over time. So it's one about spatial times. Are you seeing what I'm seeing? Hopefully, it's not always clear. No, it says paused. That's strange. You see it now? Yeah, it's interesting. So yeah, you can sort of sit across there. If you click on any individual ones, it'll bring up a lot more information about it. So you get, I mean, don't look at they're being changed right now, but you're seeing the idea about control variables. So thinking about your variable, here's a bit of experimental design for you. So what's the variable, how that variable is being used to measure where we are on that particular one. So you can also drag this graph across as well. I think you can click on the dot point, so that's where the data is from. It gives you a little bit more information about it. And there's a bit of text there in terms of some of the links as well. So, there's a bit of a glossary coming as well. There's some terms, and don't look too closely at this one because this is not out there yet. But we've started to also look at some curriculum links. So this is what's being built at the moment. Like, close your eyes, you're not seeing this, but this is being built right now, where you can click on any individual one and it'll make content descriptors. So imagine, this is like the curriculum links that it should be in the curriculum. So these are written as content descriptors that address how one links to another. And then the other one, so that might be a good one for students. The one that we're building right now is looking at all the different topics that are in a standard secondary or undergraduate chemistry curriculum. And again, the same idea, how they're connected to each of those. So let's say you were looking at acid rain, and then there's going to be some statements that one's fairly short. We're rewriting them at the moment. Linking biosphere integrity with acid rain and so on. So, we're really building this up at the moment, and we're really hoping that it's going to be something very useful for teachers and students, because sometimes it's not immediately obvious why this is something we were talking about in chemistry curriculum. So this is how we do it. To go a bit more into that, I thought I'd show you some of the stories that perhaps, I think it'd be really great for you to focus on in a chemistry classroom. I mentioned the nitrogen fixation already. So nitrogen fixation is definitely the one that we're most worried about. If following on from Doug McFarlane's talk on Wednesday, thinking about how actually now by far humans are contributing to nitrogen fixation far more than occurs naturally. An example, and so to the point that nitrous oxide, human emissions, essentially have increased 30% pretty much in this generation. And 43% of all emissions now are really from human sources. So it would be a mistake if we were to lead lower secondary students or even upper secondary students to look at that nitrogen cycle picture and go, look, denitrification and nitrogen fixation, and look at the bacteria doing their job. If we don't really show that actually humans are by far the biggest part of that now. There's a project called the Global Carbon Project. And this is one of their this is a Creative Commons source. You can find it online for your students, where they did a nitrogen oxide budget. And so you can see on the left there all the anthropogenic sources. So from agriculture, as Doug said the other day, from fossil fuels, indirect, then the natural sources. Like, no one's saying, of course, there are natural sources of these, but now and there's a sink, in other words, the atmosphere, but there's clearly now an imbalance. And why are we so worried about nitrous oxide? Well, nitrous oxide, for the most part, has a longer atmospheric residence time and over 300 times the global warming potential of carbon dioxide. How can you link that to a chemistry classroom? Well, I'm going to skip down a little and show you another one. I'm going to come out another resource. Maybe you've heard, so another one that the King's College of Visual, so go to that website, definitely. One they previously worked on was visualizing the chemistry of climate change, or VC3 Chem. And I'm going to show you why. So we just had a question on the exam looking at infrared spectroscopy. Yay, isn't it great when students sort of know where those bands are? And so this is showing what I'm showing you on the screen, which I'm not showing you. This is one of the applets that's available on that website that I'll show you. And so this is looking at that line there is the black body curve. So that's the energy that's being essentially emitted from the Earth back out into the atmosphere. And so on a good day, if it doesn't want it, it should be going out into the atmosphere. And so I put carbon dioxide on there right now. And so the reason why the global warming potential of carbon dioxide is 1, relative to all the other ones, is because it doesn't really absorb much energy in the bit where at the wavelengths that the Earth is emitting its excess energy. But it's not the same story for some of the other ones. So the reason why we're so worried about N2O is, look at that there. Look at its major infrared absorption, sorry. So it's absorbing a lot of energy in that sort of area where the Earth is emitting energy. And so if rather than the Earth being able to emit that energy out into the atmosphere, it's being kept up by N2O, and it's essentially heating up. Well, it's heating up our environment. We're particularly worried about that one. We were very worried about this one, and that's why we banned them. They were banned in the Montreal Protocol, but I've got to turn some of these off now because they get a bit hard to read. And so a lot of those ones there, so that was replaced. These were all banned by the Montreal Protocol, and they were replaced by hydrofluorocarbons, which weren't banned. These were actually seen as the better alternative. And yet here again, same problem. They are really, really, really high global warming potential. So we're well beyond the point where we now also need to ban these. I should get back to my slides, shouldn't I? So yeah, that's a great applet that you should go. I'm going to give you all the links in a second. In terms of the ozone as well, ozone is currently in the green area, and ozone is often the good news story. We often sort of go, Kyoto Protocol, isn't it great that we banned CFCs and we got rid of all the hydrofluorocarbons, and so we were really worried. Across that 70s to sort of the mid 90s, we were really heading in the wrong direction. The ozone was being dramatically depleted by the use of those, and so we banned them. And we did, yay us, we went down, we started going up again, and as if we'd solved that problem. But we didn't. Nitrous oxides are really now the dominant ozone depleting substance in the 21st century. This data only goes up to 2009. It's now starting to go the other direction. In 1980s, as I said, CFCs were by far the biggest one that was depleting the ozone environment. Now, in 2008, it's most definitely N2O, nitrous oxides. So that's really, all these came down, but now we just, replace one problem with another. As we say in the systems thinking circles, yesterday's solutions become today's problems. They've sort of started to forecast this out in terms of, you can see, through the 20th century, CFCs were by far the biggest problem, but now we're starting to really be worried about N2Os, and we don't really know. What about climate change? Maybe you played with this one, looking at sort of the energy imbalance, and I showed you that story already about infrared, how you can link that to infrared spectroscopy. But methane is another story that, wasn't it? Methane was almost in the news, wasn't it? When we started talking about how we should really be, CO2 is a huge, big problem, but another part of our anthropogenic emissions problem is CH4, is methane. And we just didn't get there with COP26. There should have been much more agreements about it, but even countries such as Australia just laughed it off. They're like, we've solved enough problems. Don't introduce another problem with this methane thingy. Let us get on with our lives. And so we're not there yet. So hopefully we have a bigger push for controlling methane emissions in the near future. All of those resources, you'll find them on the King Centre for Visualisation in Science, so KCVS.ca, CA for Canada. I've just taken a snapshot of just some of those applets that are on that website related to chemistry and related to climate change. As you can see, there's so many. I don't have enough time to show them all to you. There's one about the carbon cycle, again, emphasizing human interactions. A great one where you can look at climate solutions. So you can toggle things on and off to see how that would impact relative. Remember, that was the one about the #1 topic that educators and students wanted in their chemistry curriculum, carbon literacy. So thinking about climate solutions. When I was still a teacher, atmosphere was still a big part of Unit 2. I know it's died down a bit, But you know, thinking about what's in the atmosphere and the role of humans interacting with the atmosphere should still be a big focus. If it's not explicitly stated in the curriculum, we need to find ways of nudging it in there, you know, through, let's say, looking at it as an equilibrium focus or looking at an energy focus. Look, there's so many other there's, you know, you can go look at them in your own time. If this was an assessment task, I wonder if, you know, I've snapped that out of the consultation draft. So again, Mick, waiting for my freshly printed new study design to confirm this, but I've just highlighted 2 of those 4 SAC topics that we're all going to have to do, right? The idea is that you'll do one of these only once across your 4 main outcomes for units 3 and 4. And so the second and the fourth one will be interesting. They're the analysis and evaluation of generated primary and or collated secondary data. So of course I can see an advantage. I am definitely a prac person as well. I love hands-on inquiry. I love students generating their own data. Definitely not saying don't do that, but look at sources like this website for secondary data. You know, the data can be plotted for you. The students can plot the data in their own way. They can look at limitations to the data, assumptions that are in the data. There's a great one, which I've managed to hide. This one there, you see that there, climate model hindcasting. The one there, third in the second row there, a fantastic example of looking at how accurate some of our previous forecasts for the environment were. So that, I think that'd be perfect for evaluation of, you know, and I think the key word there is or secondary data. So you could have a SAC that's all around working with secondary data that could be from websites such as these. And then the last one, obviously, a case study or a social scientific issue. Well, are there any bigger social scientific issues for students than climate change, than sustainable development, than use of materials? Where are you going to go get some ideas? Again, go to our website. I guess I think I haven't actually put it in the chat. You know, Mick suggested that I would have done it about 5 times by now, but I haven't. You can go to the website. We ran some outreach back in 2019 and 2020. We put up all of the pracs that we designed up on there, you know, linking to endangered elements. So elements that are considered finite now. And, you know, if I had a longer time to talk with this, I'd give you the story about we are the generation, you know, that has microelectronics, and, you know, we're so reliant on them for our daily lives. And so this is the technology age, but what if we're the last generation of that age? What if the next generation after us doesn't have electronics because they don't have the elements to build them? We wrote a paper in Lab Talk, and it spoke about some of those articles in last year's Lab Talk if you're interested. Endangered elements, it's going to be in the curriculum. You know, you'll be expected to talk about this in Unit 1. And you know, rather than doing an elements poster, you know, this element has this many protons, this many neutrons, these are the ions, you know, do something more interesting. You know, why are these particular ones considered endangered? Where and what are they sourced from, and what are they used for? And the so what question. So what can we do about it? We've done this with a few classes now. We've done it with our pre-service teacher at Deakin, where they had to make a poster. But it was more to a non-scientific audience, you know, make them more aware. And so it was an assessment task where, you know, imagine you putting these up on bus stations and stuff like this, you know, making people aware about how it's a problem, why it's a problem, and so what are we doing about it? And so this is that dinosaur saying, save me from extinction. Aluminium is a great one. I'm out of time, aren't I? But aluminium is certainly not a finite resource. It is, after all, about 8% of the Earth's crust. But a fantastic demonstration to do with your students is the thermite, mini thermite reaction. It's a great chemical reaction. Aluminium plus iron oxide goes to aluminium oxide plus iron. But it's also a fantastic way to show that so much energy goes into making aluminium, It's about 3% of all the global's electrical energy supplies, and therefore 2% of all CO2 emissions in the world. And so you can release all that energy by getting it to react. And yet recycling would be 5% of the energy requirements. Concrete has been our big push this year. We did pracs with concrete. We had all of our pre-service teachers do it. We ran a graduate certificate for out of field teachers across Victoria. They did the prac. I now know of at least 2 schools who have done it. I'm presenting at STAB VCE Chem with 2 fantastic teachers. If they're in the audience, Maria and Janin from Aquinas College, they're going to show what they did doing this prac. I think it's a fantastic prac for lower secondary. I can see some connection to it, perhaps for Unit 1, thinking about materials and perhaps as an exploration topic in the Area Study 3. Again, I'm guessing. It's about guided inquiry. It's a control of variables. There are all these different variables. Concrete is pretty much made out of 4 things: cement, sand, gravel, and water. And all 4 of those are considered a finite material, or they could be, we could use something else. You could use plastics to make concrete. So we did that. We tested out different replacing things. Using glass sand instead of sand. Sand is, after all, the #1 used material in the world after water, and it is also the #1 black market material. It's by far the biggest thing on the black market because countries need it for their concrete. Australia sells sand to Saudi Arabia. Just always let your students know that fact and just spin your head. And so really just right now, there is we've put an article in the current lab talk, which is there. And if you can't get access to it, just send me an email. And wait, is there anyone from STAB in the audience? I'll send you a PDF copy of just that one there. Anyway, and I should wrap up. So our last thing that we're doing at the moment is a new project with Macquarie University, working with some industry partners. They're doing all the things up in New South Wales. A few different experiments have been designed with First Nations scientists, looking at local energy for global futures. So dye-sensitive solar cells, bioalgae, smart gardens, water filtration, probably more for the primary students. And we're in charge of doing it with Victorian schools. We don't have any Victorian schools lined up for term 1 next year. So it's very much, if you are interested, send me an email. We will come out, we bring all the material with us, we do it. We'll probably send some things to you ahead of time to do things with your students before you come. We're very much, however, looking for low SES schools and for rural and regional schools. For those endangered elements pracs that we did, we were driving 4 or 5 hours, Wodonga, Nil, Bright, as I said. Some of the other places are so far away. It was a lot of fun. And so these are opportunities that these schools generally don't get. So we're not interested in going to a school nearby. We want to go far, and it is free. So really send me an email, or maybe you know of a school who would be interested. So, forward that email, please. And there's the website. And then look at more resources. As I said, there's a lot more stuff coming out. We've got a little bit, there's an article, there's a link to that article there that explains some of the other ways that chemistry's role in the 21st century could be better explained to your students. And for that matter, teachers. Because if I was to end on something, I was a little, I was really impressed. I know many people in the audience probably weren't as impressed as I was. I was really impressed by the consultation draft. It wasn't perfect, not by a long way, but it sure did have a lot of sustainability. And so I don't think it'll have as much, the final version won't have as much. Even I might say, okay, it went probably a little too far. But, if this is going to be a priority for us in the 21st century, it would be folly. We will simply, we will evolve into unnecessary, being obsolete if chemistry doesn't, and secondary sciences don't demonstrate that they take this seriously and it's a priority, and so it's included explicitly in their intended curriculum, students won't choose this subject for much longer. They will, because universities are doing it. Universities offer programs focusing on sustainable sciences as a major, want to have a master's of sustainable sciences. Universities have gone that way. I find it odd that perhaps, and environmental sciences, the VCE environmental sciences, year on year are getting more and more students. And so we could become obsolete as a VCE chemistry if we're not more careful with how this is marketed to our students. There you go. I've pontificated. Thank you for your attention. I know it wasn't as interactive as perhaps we hoped it to be. But yeah, I'm happy to hang around for a few minutes and take any questions, absolutely. Or even look at the chat.
Yeah, thanks very much, Shaman. Seamus, has anyone got some questions? Serena has asked something in the chat. But anyone else who's got questions, you can just turn your microphones on and call them out.
While you're thinking of something, I've just put for the third time, there's a PDF copy of the slides. I know, Carolyn, I could see you sort of taking photos, but there's and that's a PDF copy of the slides, and all the links that were in there, you should be able to just grab those links straight from there. Yeah, Mel, I'll tell you a quick story. The thermite reaction, we just, it just got, I've sent the proofs off. We've written a paper about that program for the Journal of Chemical Education. So yeah, we had that lab talk article last year. We've written something for the Journal of Chemical Education. It's been accepted. I was dealing with the proofs this morning, and so it'll be published next week. But about a month ago, when we had the reviewers' comments, so get sent out to peer reviewers, and one of the comments that came back was, I think this is too dangerous. We should not be, because we had a photo of it. The photo was in the article, and they said we should not be, encouraging teachers to do such a dangerous experiment. And I said, yeah, first of all, not an experiment, demonstration. First of all, the photo doesn't show that the students were standing 2-3 meters away. And also, more importantly, we were following to the letter the practical instructions set out by the Royal Society of Chemistry that clearly state to not do it in a fume hood, because that was one of the comments that the reviewer made, to do it inside, not outside, because obviously then we're not in the wind. So all these things, and so we were clearly following, and so we stuck to our guns and we put it in there. And so, yeah, I think it's a fantastic example. It's perhaps one that we used to do a lot more in the past, but, we've taken it out. Well, bring it back as an example of sustainable science. Aluminium is something we really need to look at more.
I've done it a couple of times.
In your curriculum.
Yeah.
Sorry,
I'll say I'm very lucky. I've done it a couple of times. And it is just, I did it with university students, but you can't get more engaging than something like that. It's just a fantastic reaction. It's not too scary. It's only scary the first time.
Yes, and definitely. And I've done it about probably 15 times now, and it's gone right 14. So one time we did, is anyone from Ballerine here? Sorry, again, we got a few scorch marks on your new carpet when some of it sort of blew out sideways, but apart from that, everyone enjoyed it. And aluminium, I skipped over it. As an example of a systems perspective, the aluminium industry, that can be a topic. You could do so much around, because alumina, to get the alumina to the aluminium, what happens with all the waste material, all that red mud that we just sort of tend to ignore, the amount of energy released from that reaction. And so where does that energy come from? What do they do with the waste energy? It's a massive, and then also recycling. Aluminium is a success story. It's the number one recycled metal in the world, copper close second. because it's relatively easy to recycle. We can relatively roll it out again, and it's very easy to work with.